When an application starts lagging, the instinct is usually to throw money at the hardware, buy a bigger server, allocate more RAM, or pay for faster hosting. But the truth is, hardware is rarely the bottleneck. An uncached system suffers from amnesia. Every user request dives into the database, calculating metrics from scratch. When 100 users log in simultaneously, this multiplies. The system forces the database to perform the exact same heavy calculation 100 separate times, bottlenecking the grid. AI coding tools often accelerate this problem because they prioritize functional requirements. They focus on simply making the feature work. Unless specifically prompted to design for scale, generated code typically creates direct database connections for every single action, leaving the architecture blind to the need for an intermediary memory layer. A system that treats every repeated request as a brand new, unique problem isn't actually processing data. It's just wasting effort. To understand why raw hardware cannot fix this, we have to look at the two metrics that dictate system survival: latency and throughput. Latency is the speed of a single action. It's the time taken for one specific request to complete, the how fast of an individual user experience. Throughput is the total capacity of the system. It's the measure of how much concurrent load the architecture can swallow before it collapses. Optimizing a database for instant latency for one user often destroys the throughput for everyone else. If a database query is mathematically expensive, the server might return it quickly for one person, but it will lock up the moment 1,000 people ask for it at once. Fast for one user does not equal scalable for many. Because hardware upgrades only move the ceiling slightly higher, the system requires a deeper structural intervention. That intervention is smart laziness, the architectural practice of storing the results of expensive operations so the system never has to repeat them. In a cached request, we intercept the user's data pull long before it reaches the database. The cache layer instantly reflects the requested data back to the source, ensuring the core database never sees the traffic. We do this through read caching, where complex, slow database queries have their final answers trapped in fast server memory for the next person to use. We also use computation caching. This saves the results of heavy math so the CPU never has to solve the same equation twice. By shifting the workload to this perimeter, latency drops to near zero and throughput capacity increases because the core database is effectively on vacation. The necessity of this layer is obvious when you look at a platform like YouTube, which serves millions of concurrent users. If YouTube fetched video metadata, thumbnails, and recommendations directly from its core database for every single page load, the global network would melt in seconds. This blueprint shows the invisible barriers protecting their infrastructure. Static assets are pushed out to global content delivery networks, while video information is locked in a high-speed memory layer. These layers allow millions of people across the planet to experience instant load times simultaneously, regardless of the distance to the main server. Planetary scale is achieved through an absolute, uncompromising refusal to do redundant work. Most digital systems are overwhelmingly read-heavy. For every single update to a piece of data, there may be thousands of requests to simply view it. The vast majority of requests hitting a system aren't looking for a new discovery. They are asking for the same truth the system already provided a moment ago. Systems achieve true speed by refusing to execute tasks. The most efficient operation is the one that never happens. You only achieve true scale when you design your architecture to permanently stop recomputing what it already knows. But there is a danger to this smart laziness. The moment the underlying reality of the database changes, that cached memory becomes a liability. This is the problem of cache invalidation, the logic required to instantly destroy stored memory the second the real data shifts. If a user updates a project status to done in the database, but the cache layer isn't signaled to clear, the system will stubbornly continue feeding outdated, incorrect information to everyone else. AI-assisted development often ignores this step, focusing on the hack of adding a cache without building the truth of the invalidation rules. This is the primary source of silent, catastrophic bugs in modern apps. Caching is easy. Keeping your system from lying to your users is the hardest problem in software. See you in the next episode.